two H's here. Something takes the H, we can use H 2PO4 minus, takes the H, these electrons move in, and we get here. What mechanism did we just do? This is a simple what? Simple E1, right? Any base will take this because basically you're taking a cation back to neutral. We're not making an anion here. This is not a anion and then a 2. You could use water, that's an aqueous base. That's just a good old-fashioned E1. Other questions about that mechanism? Here's the product from above. Chromium trioxide, excess, and acetic acid. What's that going to do? Secondary oxide gets oxide. This is turned a little bit. That becomes what? Ketone? What does that become? Carboxylic acid? How we doing? Samuel? Yeah? Good. Was there any other possibilities there? Did anybody get something else? I wonder why not your product. What if we take that and react it with tosyl chloride pyridine? What does tosyl chloride pyridine do? Converts OH to a tosyl. Now, some of you in the lab report said that would convert an OH into a chloride. I mean, this gives you tosyl, and there is a Cl minus remaining there. And some of you said, well, this will come in and kick that off. Theoretically, that's okay. It could. But please be aware that it's a simple tosyl chloride pyridine gives a tosylate. Now if we come in with sodium azide, azide is a good nucleophile. You can show a full Lewis structure. One of the nitrogens has a lone pair. Basically, it does an SN2, and we get, basically we're just replacing ultimately the OH with the tosyl. Make the OH a better leaving group and then do an SN2. What if this was bold there? What if it was, some stereochemistry was defined? Because it is a chiral carbon. What would the bond to the N3 be? Yes, it would be dashed. What if we wanted the bond to be bold over there to the N3? How would we do the reaction? How would we get bold N3? What do you want to do first? What if you wanted the bold over there, the other NaCl on the top? Wanted tosyl chloride? Why tosyl? Okay, well, tosyl chloride and then what? And then NaN3? So you're saying you do the same thing, you get the other one?
Didn't you use KCN?
KCN?
NaN3, two substitution reactions in the strong nucleophile?
I didn't hear you.
Because you need it to stay bold, so you need two substitution reactions, so you need two strong nucleophiles.
Okay, so tell me the two reactions you want to do. What's the first reaction?
You could use KCN.
KCN
Yeah.
as the first reaction?
Yeah.
CN is a cyanide. I mean,
Right, so it'd be after the nucleophile.
I'm not quite following you. So you want to do KCN. KCN will not react here. I mean, that's not a good leaving group. You can't substitute it with nucleophile. Matt? Dominique? SOCl2? What would that do to the OH? Socyl will convert that to dashed chloride, right? Because the mechanism for the thionyl chloride is activation, the chlorine does a backside attack. That gives you your first backside attack. Then from the dashed chlorine, what do you want to do? Then come in with NaN3. Yeah. See, here when you make the tosyl, there's no change at the carbon. You just make the leaving group better and then you substitute. Here, if we convert it to a chlorine, which by the way is a good leaving group, or you can do PBr3, that conversion has stereochemistry at the carbon inversion because it involves a substitution. Right? You look at that, yeah? You need two substitutions. But KCN wouldn't do anything. KCN would not react with this alcohol. It might react over here, but we don't know carbonyl chemistry yet.
So you use HCl?
HCl instead of what? Instead of this? Would HCl convert this to this? It could. You just hope that it would do an SN2 instead of SN1. If you do SN1, then you're going to get racemic, and then you're going to have racemic over there. As long as it would do SN2. Thionyl chloride tends to do SN2 better. That's why we use it for like primary. It is a secondary alcohol. You could use HCl. It's just not a great reaction practically in the lab. Theoretically, it might be all right. Okay, synthesis of that molecule from bromobenzene. Hopefully you kind of knew what bromobenzene was. We've been in other problems. We'll start aromatic chemistry next week. Benzene, this is just bromobenzene. What type of functional group is in our product? Main functional group? Ether. How do you make ether? Williamson ether synthesis. So I'm going to go back. Okay, I can make O carbon bond here or here. Which one do you want to make, left or right? I'll actually do either. The one I said is I'm going to make this bond here. I'm going to make it from this alcohol reacting with some 2-carbon fragment with a leaving group. This alcohol, 2-carbon fragment with a leaving group. But when I do this, when I come forward though, what do I first have to do to the alcohol to get it to react in a... You got to remove the H. How do you want to do that? Sodium or sodium hydride. Make the alkoxide, right? And then boom, we do an SN2, we get a bond over there made. And we can get our final product. Now, as you work backwards, you like to break your molecule apart. Ultimately, we got to go back to just this fragment, a very small fragment. Now the goal is, how do you make this alcohol? Because if we can make that alcohol, we know how to make that. Well, a great way to make alcohols, especially if you want to bring in 2 bigger fragments and combine them, is what? Oxide chemistry. Can you find a nucleophile carbon-carbon OH? Yes. I can make that bond there by bringing in this nucleophile and this epoxide. Make this bond here. This came in, kicked off the oxygen. So if we back it up, the oxygen used to be bound there. And that was gone. Now that right there is an epoxide bond I tried to make there, called a banana bond. All right? Boom. That is that, and this is the nucleophile. So we can back it up and say, if I have this Grignard, which is essentially what? It reacts as if it's that, and this, which carbon is it going to attack, left or right? it don't matter. Boom, kick it off. We get this, actually get that as an anion, right? If you want to put the H on, you have to throw in acid. Instead of throwing in acid, we could just throw in ethyl bromide and maybe get that. You see what I mean? Why throw in acid when you want to turn around and take it off? But it's okay. How do you make Grignard? Bromobenzene with magnesium, right? And there you go, back to there. How are these looking? Getting more comfortable with these? One below. Questions? Okay, how do you want to make compound B? What reaction can you propose to give compound B? I see a ketone and an amine. Have we talked about how to make amines? Not just there. Have we talked about how to make ketones? How do you want to make ketones, Stanley? Oxidize what? What type of alcohol? A secondary alcohol? So if you had this alcohol, could you convert it to that? Yeah. Using one of the big three or PCC. We'll do that. Right? Doesn't the big three or PCC convert a secondary alcohol to a ketone? Now in practice, you got it may do something with this nitrogen, but you guys don't know that. I wouldn't expect you to worry about that. So it's okay here. Does everybody agree that if you have this alcohol, you can convert it to the ketone? Is that where everybody went back to? Did anybody have another place to go back? I mean, we could do this. We could say if we had a 100 carbons. If you had this, could you convert that to a ketone? We'd have to cleave off the carbon and that become carbonyl. How would you do that? Yeah. I mean, if you had this, you could treat it with ozonolysis and that would become an oxygen and you would get that. The problem is, typically when you do multi-step synthesis, you don't want to go back to more carbons. You like to go back to the same number or less. Because at this point, you got to say, well, how am I going to make the alkene? Okay? I'd suggest going this way, the redox chemistry. Now, if we have this alcohol, how would you make that? I don't know if I've ever said it before, but do you recognize a carbon-carbon OH? Nucleophile, carbon-carbon OH. So the oxygen used to be bonded there, and the nucleophile came in and kicked it off. We can back up to the oxygen bonded here. What would be the nucleophile? Just that amine? Who got this? Good. Anybody else? Good. Somebody tell me where you got stuck. Or at where? You showed this, but you didn't know how to go from here?
Right, I keep forgetting that the carbon as alcohol attached to counts as the carbon-carbon.
Anytime you see an alcohol, as long as it's got two carbons, it can come from an epoxide reaction. Like that right there. How could you make this from an epoxide reaction? Carbon-carbon OH, right there. I would have to have a 3-carbon nucleophile in the form of what? Grignard, and I would need what epoxide? I would need that epoxide. And so the nucleophile, which is that anion, carbon, when this gets pushed off, that becomes O minus, we work it up with acid, that becomes, okay? Oxides are very versatile. Matt?
I know you said this before, okay, can you explain again why you can't use H2SO4
H2SO4 where?
when we're making the alkene?
Over here? Let's get over there. Okay, so we need this epoxide. If we got that, we can bring that in. How do you make epoxides? Alkene. So if you have this alkene, do you know how to go forward? Yeah. How do you make the alkene? You're asked to start with this. Can you convert this to an alkene? We can dehydrate it, put in the alkene. How do you want to dehydrate this to the alkene? Aquapyridine. The question was, why not dehydrate this with H2SO4? What would be the mechanism, Matt, if you used H2SO4?
E1.
E1? And E1, what are you forming in an E1? Carbocation. Do you want to form a carbocation at that carbon? It's a primary carbon. I would avoid carbocations there. So why do you want to say sulfuric acid? Does it have to be an E1? What type of... We got to eliminate. Do you want to do E1 or E2? E2. Primary alcohols have to be eliminated by E2. That's when we cover tocopyridine if we're doing an E2 elimination. You could convert it to a bromide and then eliminate by use a strong base. But you can't eliminate this with a strong base because to make an OH a better leaving group, you've got to activate it somehow, like with an acid proton. Or with POCL. Was there other questions?
Well, you want us to show both the reverse arrows and the forward arrows?
No, you don't. You actually don't need the reverse arrow, but I would highly recommend it. Because this means you're thinking going backwards. Okay, how do I make this? What molecule would give this? I went back to this molecule. This is my thinking. I'm going back to this. But when I come forward, it involves reacting this with this and coming forward to give that. Okay, guys, let's see what we need to do here. Lab this afternoon. We'll be doing an NMR lecture. Any questions about the NMR sheet, the blue sheet? Posted upstairs. Next week in lab, we're moving on to aromatic chemistry. We do an halogenation of sulfanilamide, the original synthetic antibacterial drug that was used in World War II. There's 3 different halogenations: fluorination, bromination, iodination. The one you're doing depends on your 927 number, or your student number. Please see which one you're to do, and then pre-lab from there. Okay? Currently, that's a lab report. I'll have to decide if I'm going to stick with a lab report or do an answer sheet for that one. Okay? An answer sheet for the dial. Question? Were there any other things to take care of? let's see, there's a couple of questions. One of them was mechanism 8 on page 7. Is that right? Mechanism 8 on page 7? There was another question when I first came in. What was that one? Somebody else asked to work the problem or something?
That was number 4.
What page, Jason?
Page 2. And it's the one on the bottom.
Now, the answer to that one's in the back, yeah?
Right.
Did you have a question about what was in the back? Have you checked the back, or are you looking for
Yeah,
some problem?
I have a question about what's in the back.
What step? What page in the back? Is it 2A?
Yes.
What question?
The alkene attacking the cation right there.
Right here. Do you see how you can make the carbocation protonate, ionize, get tertiary cation? Okay. Carbocation, which is an alkene. That's just styrene, right? The alkene can just attack the cation. When it does, these electrons attack cation, the plus here. That's just organic 1 alkene chemistry, right?
I guess that's we never saw.
You did alkene chemistry in organic 1?
We did, but we never saw something like that.
You never saw a alkene attack a cation?
No.
Like H plus, you never reacted this with H plus? You never reacted an alkene with H plus in organic 1? You never reacted that with like HBr to give this with HBr adding to the alkene?
Yeah, that. Yeah.
But that involves reacting with H plus.
Mhm.
Well, how about a C plus? It's the same thing. I mean, it's a cation. It's the alkene attacking the cation. You react with H plus. Do what? You didn't do a mechanism for reacting alkene with HBr? Okay. Do you see it? That's what it is. It's analogous to attacking an H plus. It's got a C plus. From there, the electrons move and attack. That's going to, as the electrons make the bond, this is going to be left as a cation because it's no longer bonded. And that's what you have. From there, did you see the rest? Looks like a hydride shift. No, it's not a hydride shift. It's an elimination to put in the pi bond.
Right. No, I mean that's great. If that's possible, then cool.
Okay.
It's the same thing with brain chemistry. We did go from the 6 member to a 5 member ring. She was one. We showed we did brain expansion, and then we showed that we didn't have to really.
Okay. Let's look at question. What page was that? The other one, page 8? Page 7. Page 7. This one, there's no answer given. How we do on this? Mena, is your question?
Yeah, I'm just having a hard time the way that I'm structured. How, I mean, I know that you have to coordinate the office.
What do you want to do first?
Coordinate the office.
Which one?
The top one.
Which one?
The top one.
Okay, let's just coordinate it. We can show that mechanism. Now what you want to do? Open up. So you want the option to leave which carbon, the top one or the bottom? Top. Let it leave the top one. What does that give? So that six-membered ring is still there. So I'm going to draw it like this. Over here, there's a double bond. Here, there's a methyl. But when this breaks away, there's also what on that carbon? OH. See, that used to be bonded where? Now, when it breaks away, we got a carbocation up here. See, this used to be bonded way up there. The bridge. See it?
Yeah, I get it now. I was just having a hard time seeing like with the oxygen, but I can finish up from there.
Yeah. I mean, very often you have to kind of figure out, okay, how is this? Does it make sense how you see that six-membered ring? And these used to be bonded. You know, I need a 3D. Boom. It used to be bonded, but that bond broke away, and it's no. Okay. From there, see if you can proceed. Basically, we got to limit. Hold on. Where's the other? There's another H. To the right. Yeah, there's no H here. Yeah. Eventually, we got to eliminate an oxygen. To put in a double bond, we actually need two double bonds put in. We can put one in by removing an H in the alkene, but it looks like we might need a hydride shift. From there, it's kind of just classical chemistry, rearrangement, eliminations, and it's all pretty classical. Just this is a little bit odd. This is a rare case where we're actually making a benzene ring in a mechanism. Okay, let's test.
Wednesday.
Yeah, I might watch the Super Bowl. I don't know. Who's playing, the Falcons and the Cowboys? Oh, yeah, okay, the Falcons and the Raiders. How about that? That'll be the day. Yeah, let's move the test to Wednesday. Any objections? Monday we'll start new material though. Okay, new material that will not be on the test. We'll start new material. Chapter 2 material is benzene, aromatics. NMR this afternoon. The other group. We may spend 5 minutes just summarizing things on Monday, and then we'll start new material. See you soon.